Hey guys, Mr. B here, and in this video we're going to be going over the chapter 1.3 notes on using measurement and scientific notation. So here we go. We're going to talk about why scientific notation is useful, what units do we often use in science, and how is precision important when it comes to making scientific measurements and calculations. All right. So, why is scientific notation useful, and what is scientific notation is what we're going to start off with. So we need to remember that in science we deal with a lot of numbers, and sometimes those numbers can be very large, sometimes they're very small. So instead of having to write out lots and lots and lots of zeros, we oftentimes will use a shortcut or an abbreviation type way to write the number, and we call this scientific notation. So scientific notation is usually how we will express some number that's really big or small as a product of a number between 1 and 10 to some power of 10. Okay, so it's going to look something like this. It will be number, decimal number, times 10 to some power, and we'll just call that exponent n. Okay, it's going to look something like that. And there can be more than one number after the decimal here. So it could be number, decimal, number, number, or something like that. But usually it's going to take this general format. Okay, so that's usually going to be a scientific notation. Here's some examples though. So for example, the number 300 million be written in scientific notation as 3.0 times 10 to the 8th. That is because there's a decimal point technically at the end of the number here. And so we're going to move the decimal, which again would be at the very end. I know there's no decimal shown in this number. Okay, there's a bunch of commas, but there's no decimal shown. If there's no decimal, the decimal's at the end. Okay, it's assumed it's at the end. And we're going to move that 1, 2, 3, 4, 5, 6, 7, 8 places over. So the decimal now is going to be between the 3 and the 0. So it becomes 3.0. And the number of times we moved it was 8 times. So the exponent on the 10 is an 8. Okay, so it becomes 3.0 times 10 to the 8th. If the number is less than 1, we're going to do the same thing for scientific notation, but the difference now is the exponent is going to become negative instead of positive. So here's an example, 0.00086. We want the decimal between the 8 and the 6, okay? Because we want it as, remember, number, decimal, number. So the decimal is going to be between the 8 and the 6. And as how many places do we have to move it to get it there? Well, the decimal's starting here, and we have to move it 1, 2, 3, 4 places. So the scientific notation would be 8.6 times 10, and now it's going to be to the negative 4th instead of positive 4th because the number was less than 1. Okay, so that takes a little bit of practice, but with enough practice, it's really not too difficult to get. So now using scientific notation just makes it really easy to work with large or small numbers, mainly because it's faster to write them out. You don't have to write out lots and lots and lots of zeros, and your hand doesn't have to get tired from having to do this all the time and using up lots and lots of paper space. So, okay, there are questions in here, but as always, there's a video of me going over those questions separately. So if you want to watch that one, you can go watch that one on your own, but we're just going to stick to talking about the information in this video. So let's keep on moving. All right, SI units of measurement. What units do scientists use for their measurements? So measurements, okay, are really important, obviously, in science. We make them all the time. There's two main things you need to remember about measurements, okay? The first one, pretty much everybody remembers, and that is that it requires a number. So if you're going to make a measurement, usually there's some number you're going to write down, okay? Most people remember that part. It's the second part that people forget, especially students, that can be very, very, very important, and that is it also requires a unit, okay? Don't make a measurement and just write down a number and forget what the unit is that goes on it. Otherwise, it doesn't make any sense, and it's really hard to interpret. So many of the units you're familiar with, like inches, feet, degrees, Fahrenheit, are not units that are used in science, okay? We use, of course, inches, feet, and Fahrenheit in our everyday lives, but in science, we typically try to stick to the metric system, and these units are not part of the metric system. So there's going to be units that we're going to use in this class that you maybe aren't quite as familiar with, but you'll have to get used to it because that's just how science works. So scientists use these different units, and they're part of a system that we call the International System of Units, or the SI system. And it's basically a set of units that is used internationally around the world. So it's not just here in the US, it's every single country in the world, which makes it really easy to communicate information with other scientists because we're all speaking the same language. Okay, when I say that, I mean we're all using the same types of units. Okay, so let's talk about these 7 metric units. They are known as base units. So the SI unit for length is the meter, which of course length is a straight line between 2 points, and the abbreviation for the meter is a small m. Okay, that's important to remember because you're going to see numbers like, 4m, and you want to make sure you know what m means. Okay, so make sure that we are paying attention to the abbreviations and the letters that go with these units. The base unit for mass is not the pound. Okay, a pound is actually not a measure of mass at all. When you step on the scale and you see how much you weigh, a pound is actually a measure of force. It's the force of gravity pulling you down to the ground, and mass is an amount of mass is the measure of how much matter is inside of an object or a sample. So if you step on a scale, it will tell you how much gravity is pulling you down to the floor, but it won't tell you how much mass is in your body. Okay, the unit for mass is the kilogram. You might be familiar with the gram, which is certainly a version of the kilogram. It's a smaller version, but the kilogram is the SI unit. Okay, there are other SI units though that are also derived units, which means that they're basically a combination of base units put together. So a prime example of this would be like volume, which is the amount of space taken up by an object. And the volume is oftentimes going to be the length of something times its width times its height. So we're going to have 3 numbers that are lengths in meters, but they combine together to give us a new unit, which we call cubic meters, and we use that for volume. Okay. The other unit you might be familiar with that is used often is the liter. We don't use gallons in science, okay, but the liter or some version of the liter, like the milliliter, is also a very common one. Otherwise, sometimes we also have units that are basically 2 units put together. So, for example, density. Density is the ratio of an object's mass to its volume. So it's how big an object is divided by how much space it takes up. And so density has 2 units on it, which is the unit of mass, okay, typically again given in kilograms. Oh, okay, maybe not. Let me do this. There you go. Okay, so density is usually going to be kilograms, because that is the unit of mass, divided by, and then the unit of volume, like we just saw on the previous slide, is cubic meters. So that's the other unit, but this can also be in grams per liter. Okay, so it can be in grams per liter, or the last one you may be familiar with is grams per milliliter. That's another common one that we see for density. Okay, so all of these are common ways that we'll use derived units for density, which is again 2 units that are put together, and so they form like 1 unit, but it's really just that they're a fraction. So, all right. Also, in the metric system, we need to be familiar with prefixes. So a lot of times in science, in the metric system in general, we have prefixes that denote sizes of these units. So the sizes go up or down by factors of 10. Okay, so we can either multiply by 10 or divide by 10. And you don't need to know all of these prefixes. However, there are a few that you should be more familiar with than others. The main ones that you should be familiar with are kilo. Okay, kilo means 1,000 times bigger. So like again, a kilogram is 1,000 times bigger than a gram. You should be familiar with centi. So most of you know probably centimeters. There are 100 centimeters in 1 meter, or there are 100 cents in $1. Milli, even though it sounds like a million, is actually 1,000. So milli is 1,000 times smaller. Like a millimeter or a milligram or a milliliter is 1,000 times smaller than a regular liter. Okay. Deci, you should be familiar with. That's 10 times smaller. So a decimal, right? When you're writing numbers and there's a decimal, every time you move a decimal, you're moving it by 1/10. Okay. So deci means 10 times smaller. And then mega and giga, you should be familiar with too. So these ones you're probably more familiar with them based on your technology and data. So mega is 1,000,000 times bigger and giga is 1,000,000,000 times. So if you have, a file on your computer that's megabytes in size, 1 byte is 1 bit of computer memory. So a megabyte is 1,000,000 bytes. And a gigabyte is 1,000,000,000 bytes. So, most of the time we just abbreviate gigabytes as gigs, right? Oh, it's 64 gigs or 120 gigs. That means gigabyte. That tells you how many bytes of memory that it can hold as computer storage. So even though you maybe don't think about mega and giga, you should know what those mean, seeing as you use them in your everyday language all the time. So now the easiest way to convert from one unit of measurement to another is using what we call conversion factors. A conversion factor is a ratio, okay, and a ratio is just a fancy way of saying a fraction. Okay, a ratio is a fraction of equivalent measurements. Equivalent means equal, okay? Oh, equal, there we go. So a conversion factor is a fraction of equal measurements that's used to convert from one quantity in one unit to another unit. Okay, and we'll take a look at what this looks like here. So here's a ratio that gives you two possible conversion factors between kilometers or kilometers and meters. Okay, 1 kilometer is 1,000 meters. We can write it as a fraction, 1 kilometer over 1,000 meters, or we can write it as 1,000 meters over 1 kilometer. And so what we can do is we can use this conversion factor with some math to convert between kilometers and meters. For example, let's say we had 8,848 meters and we wanted to know how many kilometers is that. All we would do is we would take 8,848 meters, and we'd multiply it by 1 kilometer over 1,000 meters. This would convert us into kilometers. Okay, this is also known as dimensional analysis. So what we're doing is we're taking the unit of the number that we're starting with. Oh, don't mean to hit buttons there. And we take the fraction that has the unit that we're starting with on the bottom. Okay, so of these two fractions that we're starting with, this one over here has meters on the bottom of the fraction. And since we're starting with a number in meters, we want to use the conversion that has that same unit on the bottom. So we take this fraction and we basically put it down here. Okay, so it's like this. And then at that point, we just do a simple multiplication problem. And the units that are on opposite sides of the fraction, so the meters on top here that we're starting with and the meters on the bottom, those will cancel. And the unit then that we haven't canceled, we have left is kilometers, which is then going to be the unit in our final answer. Okay, so this, again, what we know is it's what we call dimensional analysis. There's a video on that though that you can watch. It's a really important skill to learn, so I would make sure you do some practice so you get it down. All right, last bit here is talking about the limits of our measurement. So what is precision and how does that affect our calculations? There's actually two words we're going to talk about here, accuracy and precision. Now, both of these words you may think are the same or very similar, and they kind of are, but they have some slight differences, okay? Accuracy is a measure of how close you are to an actual or true value of what you are trying to get. Precision, on the other hand, is how close a series of measurements are to each other, or another way to put it, and this one isn't worded in here, but I'm going to put it in here. We'll do it in red. We'll say, or how many places after the decimal you are confident in reporting. Okay, so again, accuracy. How close your measurement is to a number that you're trying to get. Precision is how consistent your measurements are to each other, or how many places after the decimal are you confident in reporting. Okay, that's precision. So basically, to evaluate your accuracy, you need to have some value you can compare your measurement to. So let's say, for example, that I wanted to know how accurate my bathroom scale was. So I just went to the doctor's office, and they have a really nice, fancy scale, and they weighed me, and I weigh 146 pounds. So I go to my bathroom scale, and I step on the scale, and my scale says 142 pounds. Now, it's certainly possible that I lost weight, but let's say I just went to the doctor's like an hour ago. So there's no way in an hour I would lose 4 pounds. In order for me to determine the accuracy of my scale, I need to know how much do I truly weigh. Okay, that's the correct value. And the value that my scale gives me then can be compared to that correct value, and that will tell me how accurate it is. So if I know I weigh 146 and my scale tells me I weigh 142, my scale is not very accurate. However, if I wanted to know the accuracy of my scale and I didn't know my body weight, I just step on the scale and it says 142, I'd have no way of knowing how accurate it is because I don't know what I truly weigh. I could weigh 142, I could not weigh. I don't know. So you need to know what the right value is you're looking for in order to determine accuracy. As for precision, you need to make a measurement more than once and then compare them to each other. So let's say I stepped on my scale 5 times. The first time it says 142. The second time it says 135. The third time it says 146. The fourth time it says 145, and the numbers are all over the place. Okay, so clearly there's probably something wrong with my scale because the numbers that it's reading aren't even the same. They're like all over the place, right? So not only is it not accurate because it's not close to what it should say, but also it's not precise because it's not consistently even giving me the same number, okay? That's precision. So precision is kind of more about consistency. Accuracy is more about being correct. Okay. So that is it for this section of notes. Hopefully that helps you. But as always, if you have any questions or confusion, reach out to me by email. You can talk to me in person in class. Otherwise, we could always do a Google Meet as well. All right, guys, I'm Mr. B. Thanks for watching, and I'll see you in the next one. Bye.